So we're going to continue with classic example 6. This one is specifically dealing with cones. Sometimes you can have cones that are facing up, like almost like the way you would eat an ice cream cone, and sometimes you'll get like an inverted cone. Sometimes they'll talk about sand piling and sand being poured in a conical pile. So with the cones, it's important to set up similar triangles because the radius and height are always in proportion to one another. So let's go through this example. So water is flowing into a conical shaped tank, and they say 5 cubic inches per second. So we're talking about the rate of change in the volume is 5 cubic inches cubed per second. Now they give you the original height of the cone and the original radius of the cone, but that's not what we're interested in. We're actually interested in the radius and the height of the water level. So when water's filling up, there's some amount of water. The water's in blue. And at this point, the height of this water level is h, and the radius of the water level is r. And I put an r here. That should be the radius of the cone, which was a base radius of 3. So what we say is that the radius to the height is always in proportion. So the radius of the water level to the height of the water level is always in proportion to the original radius and height of the cone. So this shows us how the radius and the height deal with one another. They ask us in the question, how fast? So find, they're saying how fast, so something is changing. How fast is the water level rising, dh dt? The water level is rising, so we expect this number to be positive. Find dh dt when the height of the water is 2 inches deep. So the 2 inches is kind of like when we hit the red deer sign at that very specific instant. We want to know how fast the water was, how fast the height was changing in that cone. So we set up an equation or a formula that relates the volume to the height. We know the volume of a cone is 1/3 pi r squared h, but here we have an r in here and we're not given a lot of information about r. So with this similar triangles up here, we want to isolate for r, which is 3h divided by 4, and this tells me how the height and the radius depend on each other. So I'm going to take my 1/3 pi, my radius is 3h over 4 squared h, and I'm going to simplify this equation up. So that would give me 9 pi over 16 times 3 h cubed, and I'll expand the constants, bring them out front, and then the h squared and h become h cubed. I'm ready to differentiate. dv dt is equal to, now I'm going to bring down the 3, and it's going to cancel with this 3 on the bottom. So I'm going to get 9 pi over 16. The 3's will cancel out, h squared. And then the derivative of h is dh dt. So in this problem, we're isolating for dh dt, which would be giving us dv dt divided by 9 pi over 16 h squared. And then I'm ready to sub in my values. So dv dt was 5, 9 pi over 16, my h was 2, and then I square it and I get 4, and then that would work out to 0.7 inches, because we're talking about a height, per time unit, which is per second. So in the cone examples, you will always set up this similar triangles. If you don't set up the similar triangles and then you're doing the derivative from this step, you got to watch that you're doing product rule. Okay, moving shadows is another specific type of example that is common to ask. So with shadows, you just got to be careful because they're going to ask you 2 types of shadows that are being formed. If they're referring to the tip of the shadow, they're talking about the entire base of the larger triangle. And if they're talking about the man's shadow is the base of the small triangle, or they're talking about the base of the shadow, we're just referring to the little bit, the little base of the smaller triangle. So in this question, you'll notice that A and B are identical, so I'm just going to cross B out. A man is 6 feet tall. I'm going to use 6 in my diagram because his height does not change. hypothetically, and he's walking away from a light that is 15 meters above the, or 15 feet above the ground. The light's height doesn't change with respect to time. Now he's walking away from the light, so if I call this variable x, I know that dx dt, and if he's walking away from the light, that distance x is getting bigger, so I'm going to use a positive number to represent that, 5 feet per second. And when he is 10 feet from the base of the lamp, or the base of the light, we want to know at what rate is the tip of his shadow changing. So when he is 10 feet from the base of the light, so when x equals 10, find. Now the shadow problem they're asking us to find is the tip of his shadow, and the tip of the shadow is the entire base of the large triangle. So I want to assign a variable for this section. I want to find dx dt plus dy dt. So before I can find dx dt plus dy dt, I need to find dy dt. So I need to set up a relationship between the variables I'm given. We're going to do that through similar triangles again. The height of the large triangle is 15. The base of the large triangle is x plus y. This is in proportion to the height of the man to the height, or to the base of the smaller triangle, which is y. And before I take the derivative and use product rule, I can just simplify this equation. 15y is equal to 6x plus 6y. I move the 6y to the other side. 9y is equal to 6x. I go ahead and take the derivative of both sides. The derivative of 9y is 9, but then derivative of y is dy dt. The derivative of 6x is 6 dx dt. I'm interested in solving for dy dt. So dy dt is 9 over 6, which is 3 over, dy dt is 6 divided by 9, which is 2 over 3. And then the dy dt sits on the bottom. And then I just sub my numbers in, 2/3. And my dy dt was, oops, I want to solve for dy dt. I was doing it right before. Oops, my apologies there. So I want to isolate for dy dt. So dy dt is equal to 6 over 9 dx dt. My value of dx dt is 5. So this would give me 30 over 9 and feet per second. Now I'm interested in how fast the tip of the shadow is changing, so I want to do dx dt plus dy dt. And that will give me the 5 feet per second for dx dt plus the 30 over 9 that I just solved for. And then that would be my final answer, feet per second. Now I could work that out if you'd want to. So 50 divided by, or 5 plus 30 divided by 9. Change that to a fraction, and I get 25 over 3 feet per second. So that's how fast the tip of the shadow is changing. Now, when we look at the last part of the question, we're talking about a cylinder. The volume of a cylinder, they remind us of that formula, pi r squared h. Now, one thing you want to notice here is if this cylinder is filled with water, over here, the height of the cylinder, or the height of the water is h, but the radius of the cylinder is the same as the base radius that I actually started with. So just keep that in mind. So Mrs. Schaub, you can change that to Miss Lacani if you want, because she does actually have a headache today. Miss Lacani has a headache from her too loud calculus class. She goes to the math office to take aspirin. The water cooler is cylindrical in shape, so we'll just use this diagram above with a radius of 10 inches. So my R is 10. and my height of the cylinder is 22. She noticed that the height of the water in the tank is 8 inches. So when H is 8, it was dropping at a rate of 2 inches per minute. So the height is decreasing at 2 inches per minute. So now I want to know how fast is the water flowing out of the tank. So we want to find dV dt when that above stuff is true. So let's take our equation. Volume is equal to pi r squared h. Now one thing you'll notice is that the radius of the water level is the same as the radius of the cylinder, and no matter when the water level is dropping, the radius stays identical. So I can take my radius and just sub it in because it doesn't change with respect to time. So this would be 100 pi times h. Okay. Now we take the derivative, dV dt is equal to 100 pi times dH dt. The value of dH dt is -2. So my final answer is -200 pi. And it's volume, so we're talking about inches cubed per and time units per minute. So the difference between the cylinder and the cones is that the cylinders, the radius doesn't change as the water level is increasing or decreasing, but in a cone, it would actually change. So that's the end of our video.